Welcome to this introductory video on C pointer arithmetic. In this lesson, we will explore how pointers can be used to manipulate memory addresses directly. This is a fundamental concept in C programming that allows for efficient memory navigation and data structure traversal. Get ready to dive into the world of pointers. Pointer arithmetic involves adjusting memory addresses based on the size of the data type a pointer refers to. A key concept to grasp is that when you add 1 to a pointer, you're actually incrementing the address by the size of the data type it points to. For example, if you have an integer pointer, adding 1 to it typically increments the address by 4 bytes, assuming an integer is 4 bytes. With character pointers, adding 1 increments the address by just 1 byte, since a character occupies 1 byte in memory. Let's look at an example. Here we have an integer array called numbers, containing the values 10, 20, and 30. We declare an integer pointer PTR and make it point to the first element of the array. Therefore, printing the value pointed to by PTR will output 10. When we print the value pointed to by PTR plus 1, it outputs 20 and PTR plus 2 outputs 30. Remember that PTR plus 1 adds the size of integer bytes to the address, and not just 1 byte. Let's delve deeper into how pointer arithmetic varies with different data types. Consider an integer pointer PTR, initialized to memory address 1000. If we increment PTR by 1, it will point to address 1004, as integers typically occupy 4 bytes. Now, if we have a character pointer CPTR, also starting at address 1000, incrementing CPTR by 1 moves it to address 1001 because a character occupies only 1 byte. Lastly, for a double pointer DPTR initialized to 1000, incrementing it by 1 advances it to address 1008, since doubles generally require 8 bytes in memory. Therefore, the increment value depends on the data type. It is 1 byte for characters, 4 bytes for integers, and 8 bytes for doubles typically. Pointers offer an efficient way to navigate arrays by incrementing memory addresses. The name of an array often acts as a pointer to its first element, and pointer increments automatically adjust for the data type size, making array traversal seamless. Both array indexing and pointer arithmetic can access the same memory locations. Let's see this in action. Here we have an array named numbers of size 5, initialized with values 10, 20, 30, 40, and 50. We declare a pointer PTR that points to the start of the array. We can access each element of the array using a for loop and array indexing. Another way to do this is by incrementing the pointer using pointer arithmetic. It is important to be cautious and avoid accessing memory beyond the array bounds, as this can lead to undefined behavior and program crashes. Now, let's explore the operations of pointer subtraction and comparison. When you subtract two pointers, the result is the number of elements between them, not the number of bytes. This is particularly useful when determining the distance between two elements in an array. Pointer comparison is valid when both pointers point to elements within the same array. If pointer 1 is less than pointer 2, it means pointer 1 points to an earlier element in the array. Furthermore, pointer arithmetic can help calculate array sizes and the distances between elements. Consider this example. We have an array of 5 integers. Pointer P1 points to the second element with value 20, and P2 points to the fifth element with value 50. Subtracting P1 from P2 gives us a distance of 3, which is the number of elements between them. Also, pointer comparison works such that if P2 is greater than P1, then P2 points to a later element in the array. Keep in mind that pointer subtraction and comparison are meaningful only when both pointers refer to elements within the same array. Applying these operations to unrelated pointers can result in undefined behavior. To ensure robust and reliable code, let's review some best practices and common pitfalls when working with pointers. Always check for null before dereferencing a pointer to avoid segmentation faults and unexpected crashes. Use the const keyword for pointers that should not modify the data they point to, adding an extra layer of safety. Be mindful of the pointer type when performing arithmetic to ensure correct memory access. Avoid common pitfalls like accessing memory outside the bounds of an array, which can lead to unpredictable behavior and security vulnerabilities. Also, refrain from dereferencing uninitialized pointers, as they may point to arbitrary memory locations. Do not forget that pointer arithmetic is scaled by the type size. Here are a couple of examples. The function printArray takes an array and its size. The first thing it does is check whether the array is null. If it's not, then it loops through the array and prints each element. Another function, displayData, takes a constant integer pointer, which means that the values that the pointer points to cannot be changed. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.